All right. Good evening, everyone, and welcome to Mount Washington Observatory's Science in the Mountains lecture series. My name is Brian Fitzgerald, and I'm the Director of Education here at Mount Washington Observatory. And joining us this evening to provide a brief update on ongoing research at Mount Washington Observatory is Summit Intern Myah Rather and Weather Observer and Research Specialist Karl Philippoff. Also joining us tonight to introduce both will be Jay Broccolo, our Director of Weather Operations, in just a bit here. Thanks so much for joining us for tonight's program. Excited to share all about ongoing research here at the Observatory. And if you're not familiar with us already, the Observatory is a nonprofit, member-supported organization with a mission to advance the understanding of the forces that create Earth's weather and climate. And the way that we accomplish that is through operating our Summit Weather Station with around-the-clock weather observation and forecasting, along with our regional mesonet, by conducting research and product testing projects, and by developing and offering innovative educational programs. If you have a question for tonight's speakers, please feel free at any time. You can use the Q&A button. You can find that right down at the bottom of your screen. And you'll be able to have some time to have your questions answered at the end of tonight's webinar. Any questions we can't get to, feel free. You can follow up with us at education@mountwashington.org. Additionally, if you're joining us through Facebook, welcome. Thanks for joining us that way. You're welcome to submit questions, but we won't be able to get to those until after the program. So by all means, if you'd like to join us on Zoom the next go around, please feel free to register for Science in the Mountains program over at mountwashington.org/SITM. Alrighty, so before I introduce tonight's speakers, I will go ahead and share a set of poll questions here for everyone who's joining us on Zoom. So if you're joining on Zoom, you should be seeing some poll questions, 4 of them pop up right now for you. First question, as always, curious where you're joining us from this evening. Perhaps it's a state within New England. Perhaps you're joining from outside of the region, or perhaps you're joining from outside the country. Love to know where you're joining from. Always amazed with where folks join in from. Next question, kind of curious, want to pull the audience here around just your general knowledge level. How would you describe your weather and or climate knowledge? Curious, going from, say, the very beginner stage, novice, all the way to advanced beginner, competent, proficient, or expert. Just want to get a feel for who's in the audience tonight. I know we tend to have quite the range of interests, and certainly our speakers love to cater their work to whoever is in the audience. And then we have 2 questions here from our speakers, Karl and Myah. The first question coming here from Myah: what year since records began at the observatory has had the highest number of precipitation on snow events or rain on snow events? Was it back in 1981? Was it 1999? Was it back in February of 2020, or even was it more recently in March 28th of 2023 here? So get your responses in when you have a second. And then last but not least, in what season, spring, summer, fall, winter, should have been that last piece there, my apologies, typo on my part, is the daily average temperature change between the base and the summit of Mount Washington the greatest? Is it spring, summer, fall, or winter? All right, I'll give everyone just another moment here to get your answers in. Most of you have already responded. Thanks so much. And we'll go ahead and close that poll in 3, 2, 1. All righty, we'll end that poll. We'll share some results with everyone on Zoom. Looks like New Hampshire well represented this evening, the highest proportion of those of you joining from any singular state, not far behind Massachusetts. But folks joining from outside the region, quite a few of you, that's wonderful, and even one person from outside of the US of A. So welcome to everybody, some great representation across the board there. In terms of how you would all describe your weather or climate knowledge, this is really interesting. Okay, competent is how at least a third of our participants this evening, and good representation across the board from novice, advanced beginner, competent, proficient, and even one of you was brave enough to say expert. I'm sure quite a few of you who claimed proficient are probably sitting in that expert column there, but your modesty is just fine. All right, and then for our trivia questions, most of you, more than half of you, thought that March 28th of 2023 had the highest number of precipitation on snow events. We will see about that. And then lastly, what season do we believe the daily average temperature change between the base and the summit of Mount Washington is the greatest? Almost a third of you said spring. Winter was in last place there. Interesting. All righty, and apologies, I may not have been sharing those results with everyone right there. Well, at that, I would love to go ahead and introduce our speakers for this evening, and to actually introduce our speakers and to give a little bit of background and context for our programs tonight and a little overview of research at the observatory. I'd love to welcome our Director of Weather Operations, Jay Broccolo. Jay, are you there? Hey, there you are.
Hey, Brian.
Hey, Jay, how you doing?
I'm doing great. How are you?
Good. You're on the summit, right?
I wish. I'm actually at my
there?
house, but it looks like I am, right? I'm
Yeah,
like with my fellow observers.
yeah, well, I'm not on the summit either. But at any rate, Jay, you can hear and see you just fine. Feel free to take it away.
Great. Okay, let me start my presentation here. All right. Okay, so my name is Jay Broccolo. I am the Director of Weather Operations, and here's a cool picture of some lenticular clouds with the sun in the background there. Brian kind of went over our mission statement, but here it is in text. We are a private nonprofit research and educational institution working to advance the understanding of the Earth's weather and climate. Not yet any exoplanets. So my goal here is to just briefly touch about some of our research areas. The first two are ones we're focusing on tonight, and all four of them we are building throughout the years coming. But just to give you a little bit of taste for them: meteorology, the study of the weather patterns and how we forecast for them, any extreme conditions that we see in the region, and the climate data. So the weather data that over time leads to long-term trends, which then we can consider climate data. And then leading to that climate science, those long-term trends, and how they change the impacts of the region, which also goes into environmental monitoring. But before we get to that, the atmospheric science, so which is kind of all encompassing of all of this, but mainly it's trying to figure out how the dynamics of the atmosphere works. So the meteorology is very much in those weather patterns, and then atmospheric science is kind of like the whole broader context, how it works together with the composition of the atmosphere, the systems involved in the dynamics, and then how all of this comes together and affects our environment. So like the biosphere. So first off, the meteorology, the study of the weather patterns. So here you see, this is from a GFS output from some winter storm, which has a pretty low pressure there. And you can see snow with the blue over here, if you can follow my mouse, the low pressure here at 961 millibars, and then an area of some pretty intense precipitation here with the yellow and the red, and these really, really close lines, which to us, the closer we see these lines, the more wind there is, because it's a pressure gradient. So essentially you can consider this like a big valley, and then wherever you see these high pressures, like the summit of Mount Washington, and then from this low to the high, you're kind of like hiking up the mountain. And that would be the same pressure level. So it changes throughout the atmosphere. And if we can understand that, then we can better forecast the weather, especially in these extreme conditions. One way we do that is through forecast soundings that the GFS can also output through different output graphical interfaces. These are called skew-T plots in the US or tephograms in the UK or in Europe. But what they do for us anyway is show what a forecasted lapse rate is. So the summit of Mount Washington sits at about 800 millibars on average. So this is about where we are on this temperature line here. One of these lines is a temperature line, and you can see at the rate at how they increase between ice pellets or sleet and freezing rain is quite similar, but there are some changes, and that slight difference can give you the different, or can give you a product of freezing rain or ice pellets and sleet. And then you come over here to the left where it says the snow, and you can see how that never actually drops below this 0 line. Now there's a ton of other lines here, but for tonight's purpose, we're just looking at the blue and the red ones. So we have a temperature and dew point temperature essentially, and where they come together, you have clouds or precipitation possibly, and where they spread apart, that's the drier the air is. But for our purposes, we're really interested in this first bottom 20% of the atmosphere. And that's where Karl's presentation will really get into, studying the lapse rates of the area around Mount Washington, at least on its eastern side. And then for climate science, we've done work with the AMC, Georgia Murray specifically, who's responsible for this chart here in her published paper. But you can see that the temperature is rising from the beginning of our temperature records up until present day. Now it's a little bit less than it is on the summit than the warming that's happening at Pinkham Notch. So that's great or not so great for us, depending on how you look at it. But anyway, so these long-term trends are really what we're interested in. And this is what Myah's research is going to get into. So she's looking on precipitation events on snow. So anytime we have a snow depth, and what type of precipitation will be falling on that. So right now we're looking at just precipitation, but in the future, we're going to separate that into precipitation types. So from here, I will let Karl and Myah take over. So Myah will be speaking first, and there's her presentation, rain events or precipitation events on measurable snow depth at Mount Washington. And then second, and then we have Karl Philippoff, establishing near-surface lapse rates along the eastern slope of Mount Washington, which is a funded project through Synoptic Data. So thank you to Synoptic. And I will now pass it over to Myah. So Myah, if you are ready.
Yep.
Great. Okay, take it away, Myah.
Okay, hello everybody. Everything set it up. Okay, hello everybody. My name is Myah Rather. I recently graduated from Penn State University and now currently a Howard graduate student, and where I'll be continuing my studies in meteorology and atmospheric science. So before I get into my research, this summer I've had the amazing opportunity to spend my time at Mount Washington. Here I've learned a lot about the extreme wind conditions. Additionally, I worked enhancing on communication skills to effectively educate others about science. And I've also learned how to forecast on the higher summits. And in addition to further developing my research skills, well, I'll go tonight about a little bit of the research I've been doing on rain and snow. And like I said, I'll be presenting that research on rain on snow and my findings this summer. But before I get into that, I do want to highlight the trivia question that you guys answered before in the poll. So what year had the highest precipitation on snow events? The answer was actually 12/31/1981. So I'm getting ready to kind of show you my data and my findings, but that's kind of just to get you guys kind of ready for what I'll be showing you guys. So for climatological trends on Mount Washington, and So the shifts in extreme and weather and seasonality. In a comprehensive analysis spanning from 1980 to 2020, I delved into the dynamic landscape of Mount Washington's climate. My primary objective was to discern the past 3 decades and have tried to witness the transformative shift in severity and frequency of weather extremes. So that is reshaping both its seasonal patterns and overall climatic averages. This investigation was fueled by two key goals, which first to determine whether Mount Washington's weather extremes are intensifying, yet paradoxically becoming less predictable in their recurrences, thereby instigating broader shifts in the climate's baseline characteristics. Secondly, we probe the intriguing question of whether alterations in these averages have become a discernible impact on the summit precipitation, specifically investigating the correlation between changing patterns and an increased occurrence of rain on snow events during the winter months. Throughout this course of the study, our focus prominently centers on rain on snow phenomena and emphasizing their pivotal role in shaping Mount Washington's meteorology, as Jay kind of highlighted prior to me introducing me. So first, I want to tell you guys, before I show you guys all the data, I wanted to go into about my methods. I analyzed and visualized the average weekly snow depth trends and precipitation on snow events from 1980 to 2020, as I mentioned. My process involved filtering the data set to focusing the time range, computing the weekly averages, and using streamlined plots from using Python. The resulting plots provide a concise overview of changing snow accumulation and precipitation on snow event patterns over the examined decades. You may be wondering why I went on precipitation on snow rather than rain on snow. And that is because of the challenges arose from the data set limited to the differentiation between various forms of precipitation. So that means that focusing on solely precipitation on snow counts was necessitated by the absence of clear distinctions between rain, snow, and sleet, and other precipitation types. So precipitation on snow actually is the period of time our precipitation value within the data set exceeded 0 with a depth equal to or greater than 1. Why did I select this? This was extremely important for the challenges, like I said, were deciphering the precipitation and me not clearly knowing if this was rain, snow, and sleet. So to overall, and to make sure that I was grabbing the right data, I wanted to analyze precipitation on snow events. And in addition to the weekly averages that I wanted to let you guys know about that I also plotted, were because our observers during their time on the summit, they actually do so 4 hours throughout the day. And these are synaptic hours that I have, and I did not want to over filter our data with just mini plots and a lot of scattered stuff is what I came up in the beginning. I wanted to kind of limit it. So I went with the weekly depth of snow depth and how it was changing throughout the months. That was the best rather than going from day to day, because much of my data was kind of had extreme like one depth for like 2 times, and I didn't want to overcount the data. I wanted to show you guys how the depth was actually changing. So that was my reasoning for going with weekly. So going into my data with snow depth, so this is average weekly snow depth in 1980 from 1990s. The start of my research, I had, like I said, a data set from 1980 to 1920. So the first thing I wanted to do was actually open up this data to see, okay, how are things changing? As you guys can see, the flat line at the bottom of all of these plots are typically during the summertime when the summit is actually reaching a snow depth of 0. So we can see the peaks of our snow depths of when things are actually changing and how actually things are changing throughout the course of the years. So these are the decadal trends. So I broke my file up from 1980 to 2000, and then this is early 2000s from 2010. And pretty much doing the same thing, the same analysis, and trying to see if I see anything that kind of stands out, as I will also compare other variables. There are a lot of things that actually factor in the snow depth on Mount Washington summit. So you have the direction of the wind, you have temperature, you have how much is actually snowfall, and there's a bunch of more factors that we do have to include in that will highlight as this research grows. But these are some of the snow depth, just the snow depth measurements that I was able to obtain for these years. So going into the snow depth climatological trends, so from the plots that you guys seen previously, you probably really couldn't figure out, decipher any extreme like things that got your attention. And that's what I noticed with my data. So I took a step back and was like, okay, let me see how things are going from 1980, 2012 to, well, 1980 to 2010, and then 1990 to 2020. And those are two climatology reviews. Climates are actually typically measured in 30-year time spans. So these are the time spans that I decided to go with. And as you guys can see with the average weekly snow depth from 1990 to 2020, we can see an increase of snow depth on our summit from then. And I was able to actually solidify my findings with this research. And I was like, okay, now I can see how things are actually changing here on Mount Washington Summit. Something that was really cool to me was definitely just throughout my internship experience, was taking a step back and actually learning Washington's climate, and also relearn the environment I'm in, as I am from Maryland. So typically I'm not really familiar with the environment of Mount Washington. So this was something cool to kind of even study, as like I said, I'm interested in research and I'll be pursuing my education, obtaining a PhD at Howard University. But it did take a lot of analysis of just figuring out what is the typical snow depth for Mount Washington? Well, how does it kind of range from different years? What are the changes as we are revealing the climatological trends? So the other variable that I wanted to partner with this, as our end goal is rain on snow, but however, I was able to only obtain precipitation on snow events, I'm sorry, before I get to that part, this is the snow depth of climatology. So this is from 1980 to 2020. This is the plot that I actually took all my data and just plotted it against the x-axis and y-axis. That is, like I said, ranging from 1980 to 2020. And these are the average weekly snow depths from this year, this time span. And that too also showed the same data that I was telling you guys about previously on the last slide. There is an increase that we do see with precipitation, snow depth coming, that we're like, okay, so snow depth is growing on our on the summit, and this is notable here. So as I move on, we have precipitation on snow trends. So for the same analysis, I wanted to conduct the same thing that I had did on the snow depth and evaluate it the exact same way. So this is from the 1980s, from the 1990s. Like I said before, it was really hard to pick out outliers and differentiate from the data of how things are actually changing. So these were kind of just opening up like decadal trends and just seeing, okay, what's happening throughout the years, what's happening on a small scale, and taking it to a larger scale, especially as you do a climate analysis. You want to see, all right, is this occurring faster than we think, or just certain questions like that were kind of going through my mind as I was creating my data up on the summit. So this is from the early 2000s and 2010, where it was really hard to see anything that really was a standout. And like I said, the reason for the precipitation count was due to the lack of not really knowing the challenges that we ran into, and limitation necessitated a focus and examination of precipitation. So in the context of snow accumulation, while this approach provided valuable insights in snow depth trends and the broader characterization of precipitation types and that. So definitely for precipitation on snow, not really being able to differentiate if it was rain, snow, sleet on what was falling. This was easier to create my function that actually deciphers if the precipitation, like I said, is greater than 0, while there's a snow depth of equal to 1 or greater than 1. This is plotted alongside these graphs. So precipitation on snow climatological reviews, like I said, I wanted to carry our variables the same exact way. So this is from 1980 to 2010 and 1990 from 2020, two separate 30-year time spans. And this gave me a better outlook of how actually our precipitation counts are changing, and if I've seen anything kind of standing out. And this doesn't really give a really good, other than 1990 to 2020. You guys can probably spot out this increase here, where things actually do kind of begin to rise over time. So these are things I was kind of looking out for. And like I said, also just getting to know the Mount Washington Observatory's climate. And okay, so what does a typical snow depth look? So a couple of my findings were as well is what a typical like the counts for them as well, of like, okay, how often does the snow, what is the average for the snow depth every year, that you also can see kind of plotted along here. And then I also did the same thing with precipitation on snow climatology. This is taking all of my files that I was able to gather and just plot them against one another from 1980 to 2020. And like I said, you can see this increase right here from 2000 to 2020, that there are more precipitation on snow counts here on Mount Washington Observatory. And the parallel with the snow depth are that, as the snow depth grows, that we also can see precipitation, rain on snow, and the precipitation on snow events accumulating. The two kind of work hand in hand. On first and foremost, we need the snow depth to be there to even estimate the precipitation on snow. So that highlights kind of our next moves. And conclusion, our snow depth trend, our analysis of data spanning from the 1980s to 2020s revealed a consistent increase in snow depth. This trend underscores the dynamic nature of snow accumulation over the decades. And for precipitation on snow counts, examining precipitation, we observed a corresponding upward trajectory. This suggests a potential link between precipitation events and snowfall patterns. As I mentioned, there are a lot of factors that either the next intern or even myself will have to evaluate when it comes to wind direction, temperatures, to understand if these precipitations that we are actually recording are actually snow or rain or you have sleet. There's a lot of things that we do need to factor in. This is kind of the start of this research. So I'm excited to do the start of everything. But yeah, so for closing remarks, the correlation between rising snow depth and increased precipitation on snow counts presents an avenue for continuous research, as I mentioned before, and for future interns engaged in rain on snow. These findings offer valuable insights into the complex interplay between the precipitation forms and the snowpack dynamics. And yeah, as I build this knowledge, I look forward to assisting future researchers to contribute meaningfully to climate science, guiding us toward a deeper comprehension of changing weather patterns and their broader consequences. I just wanted to thank you guys for listening to my research and the things that I actually conducted on the summit. My apologies. But taking a look into Karl and his research and what he also too got over this summer. And next up is Karl.
Sorry. Let's try that again.
Oh no, Karl, you just had it.
They working?
No,
Oh, still not?
no. I have it queued up on my screen. If you want to give it another try, just let me know.
Okay, let's try one more time. Okay.
I mostly see that, but also seeing a little bit of a browser view. You want to try advancing the slide one?
Working?
I'm seeing your second slide, and I'm seeing the browser bar above it as well, but I think I am largely seeing it otherwise.
Okay, well, let's see. Let me just do a new share. Stop share. One last time.
Still seeing the browser view.
Hmm.
You want me to
Yeah,
share it? Yeah. All right, feel free. You can stop sharing on your screen for a second there. And hopefully I will get this right. Can you see that okay, Karl?
I can see that fine.
Great. Just let me know. You drive it.
So I'll just say like advanced slide type thing.
Sounds good.
Okay, so I am Karl Philippoff. I'm a weather observer and research specialist. I actually was I started as winter intern this January on January 4th actually, and I heard that my shift was actually looking for an extra weather observer, so I threw my hat in the ring, and I managed to get hired actually in February, right after our record cold event. So without further ado, I started researching near-surface lapse rates when I actually started at Summit. And I'm going to present to you some of the findings that I actually found over the last few months. So next slide. Okay, so actually Jay kind of covered this, but okay. So the question we were looking for was what are typical near-surface lapse rates on Mount Washington, and how do they vary on daily, monthly, and annual timescales? And not only just on Mount Washington, but also how that might apply to the broader Northeast and New England region. And so the primary objective was to establish a baseline for average lapse rates expected at different timescales, as well as some measure of their variability about those averages. So looking at those daily, daily, monthly, seasonal, and annual averages. And then try to attempt to apply that actually to ongoing research within the White Mountains and greater New England area to deal with temperature variation with elevation. So that would be useful in the ecological and snow hydrological and other types of research. So keep going. So first off, before we discuss this any further, what is a lapse rate? A lapse rate is actually usually in meteorological terms is usually a decrease in a variable, typically temperature, with increasing altitude or elevation. And notice that I have the plus or minus delta T over delta Z. So delta T being temperature and delta Z being elevation. And the plus or minus is actually due to, depending on the research study you look at, sometimes those lapse rates are negative, sometimes they're positive. They're expected to be negative, so sometimes they actually use it positive, but it gets a little confusing with sign conventions. And just actually one other additional point was, why does temperature generally decrease with elevation? This is actually has to do a little bit with thermodynamics, which is a big scary phrase, but I'll try to explain it as best as possible. So as an air parcel, if you have like a hot air parcel and it kind of ascends from the high to low pressure, so as you go up in the atmosphere, pressure is decreasing, that parcel actually expands. And as that parcel expands, it actually does work against that air that it's actually pressing against. And as long as it doesn't exchange any energy with that air that it's pressing against, it actually causes the temperature of that parcel individually to decrease. So which is actually why in the troposphere, in the area of the atmosphere that we actually are in, that's why typically why temperatures actually decrease with height. And so if this happens to dry air that's not condensing, it's called the dry adiabatic lapse rate. And because of actually gravity, that decreases at about 9.8 degrees Celsius per kilometer. And for moist adiabatic, so if that air is actually condensing as it's expanding, it's actually a little bit lower because that water vapor is actually providing that air mass with a little extra energy. And so it's usually a little bit lower than 9.8. And so typically in a typical atmosphere, it's about 6.5 degrees Celsius per kilometer, but it can actually be quite a bit lower or a little bit higher depending on the moisture content of that air. And so when I say greater lapse rates, that means they're more negative, so that there's a sharper decrease with height, so there's a more difference between base to top, and a lesser lapse rate is less negative, which means the shallower decrease with height, so that temperature variation is not varying as strongly with altitude. Next slide. Okay, and so the other difference that I said I was studying near surface lapse rates versus free air lapse rates. And so near surface lapse rates, you're basically looking at the top screen, you have like this Stevenson screen. So you're looking at temperatures that are always about 2 meters above the land surface. And so this usually for near surface lapse rates, you're looking at mountainous regions, so that places that have significant topography or complex terrain. And so you're looking at temperatures that are varying along that slope of that mountain. Versus free air lapse rates, which is below, you have like the radio sound, you're actually releasing those from weather stations, and they're going right up into the atmosphere. And so the influence of surfaces is actually quite important. because the difference between a surface characteristic versus the air characteristic is actually quite a bit. Because surfaces, usually land surfaces, are where you have radiation exchange. So you have like incoming solar radiation. You also have that long range radiation that's coming in, and then it's being almost transformed at the surface into sensible heat and latent heat and different kinds of energy. And so that kind of exchange is kind of makes it kind of a unique kind of area of the atmosphere. That's where a lot of land surface hydrology and all that kind of stuff actually happens. And the surface is also where organisms are. So that's like the botanical and ecological impacts are felt. So different organisms like animals or like us actually feel that kind of difference versus in the free air, there's a little bit less direct relevance to us. Also, in addition, especially for snow hydrology and glaciers, those surfaces are actually where that energy exchange is happening. And so actually that's where they're melting. So if temperatures at the surface are above freezing, that means they're going to be melting. If the temperatures at the surface are below freezing, then they won't be melting. Whereas temperatures in the upper atmosphere, or at least a little bit above the glacier surface, actually won't have quite as much of an effect on those kinds of characteristics. Okay, next slide. So how is this research typically done? So generally for ecological and snow hydrological research, you usually have stations that are roughly at the base of those valleys and in the mountainous regions, because it's a little bit easier to access them. And there are also typically more people living towards the bottom of those elevations. And then they take that kind of measurement and they kind of extend it up those mountain slopes based on either an estimated or a theoretical lapse rate. So in the absence of local regional data, many researchers have used what is called a standard atmospheric lapse rate of about 6.5 degrees Celsius per kilometer. And that standard atmosphere lapse rate is kind of a global average that's around the whole world. And so it can be pretty good in some locations, but often is not good in many locations, especially if you're looking at point measurements. And so then they use they basically use that lower station data to try and then use high resolution elevation data to actually kind of fill those temperatures in into like a kind of a distributed model. So you have like usually like one or a few measurements, and then you kind of fill in the whole broader region to kind of show you how temperature variation actually happens with height. It's especially for really fine scale research. So definitely for ecological research in mountainous terrain, or especially for snow hydrology in the West, and also even in the East Coast, where that snow actually really it's a lot quite different at the valleys versus at the top of the mountains. Okay. So for this study, the data used, we're using data looking at between January 1st, 2016 and December 31st, 2022. And so this is on the right is actually a screenshot of the current conditions page. And so that box right there is our the autoroad vertical temperature profile. That's our stations going up the autoroad. So if you've ever been up to Mount Washington, if you looked up to the right and left, you see those mesonet stations. And so those are live streamed, the current conditions page. That actually is a live representation of the temperatures as you go up the mountain. And so those stations are all roughly on the leeward side of the mountain. So they're all on the eastward facing. So leeward meaning our prevailing winds are from the west-northwest, and the autoroad's predominantly on the eastward side. And it's also actually so eastward side also is important for when that sun actually comes up. So the sunrise actually happens a little bit earlier on the east versus the west side of the mountain. And also importantly, that the data is actually relatively consistent and of excellent quality. So for all those stations, I believe like the 4,300 foot station is like the station that is the most or least complete, and it's still about 98 to 99% complete, whereas the other stations are almost 100% complete over that entire 7-year period. And also another important thing to note about this data is actually that you have a singular basin elevation. So like that, the Pinkham Notch is all those stations are roughly stacked right above Pinkham Notch, which helps make the data analysis a little bit easier. And also all those stations are in a very small spatial area, so they experience the same weather at nearly the same time. So all these things are actually good for measuring or getting a good case study for lapse rates within the New England region. Keep going. Okay, so the methodology. So we were looking at each station data. We took out temperatures that were above or below the New Hampshire state record. So any temperatures that fell above 106 degrees Fahrenheit or below -50 degrees Fahrenheit, or in any days where temperature variation at a single station was greater than 100 degrees Fahrenheit. So I mentioned that we had excellent data quality, and those actually didn't really affect the data all that much. So if any days that had a significant amount of data points that were above or below those extremes, they were excluded completely from the data set. And then based on the ones that were retained, you determined the maximum, minimum, and the average temperature at each station for each day. And based on that data, you kind of see that the plot to the right. And so basically, it wasn't actually that many points. There's only 7 stations. So this is just a hypothetical plot. But based on those 7 stations, you actually fit a best fit line through that. And that line, that slope of that line that is on the resulting plot would be your lapse rate. And so you can do that for your maximum temperatures, your average temperatures, and your minimum temperatures. Typically, that's just basically how research for lapse rates is typically done, mostly because the data that most other researchers are using is much more time sensitive. So they're looking at hourly to daily data, whereas ours actually is down to the minute data. But to make it more consistent with other researchers in this field, I decided to kind of condense it to about daily averages for the most part. And then also, in addition, we actually examine temperatures every 10 minutes. So looking at the whole 7-year period, I basically figured out at midnight, if you average the temperatures for all stations, or for one station, the average temperature at midnight was X temperature, and then kept going through every 10-minute period throughout a 24-hour interval, and looked at how temperatures varied over that daily cycle. Next slide. So looking at those daily cycles, so again, these are constructed by taking averages every 10 minutes over that 7-year period. And so over that whole period, you basically can see that as like basically a solar day. So from midnight all the way to midnight. And so you can see the different colors on that plot, basically showing you the different elevations. So that legend on the right. And so the lowest elevation station is all the way at the top. It's got the highest temperatures. And the summit's elevation is all the way at the bottom. That's showing that lowest temperature. And so if you actually, so this is because over a 7-year period. And so if you actually, so there's 144 10-minute periods within 24 hours. So if you actually added up each of those temperatures at each of those points and you took an average divided by 144, that'll actually get you the annual average at that location for that 7-year period. And so the other thing I want you to notice about this plot is that since they were eastward facing plot, they're eastward facing stations for the most part, that you see like this rapid increase probably between about 6 and 9 local standard time. And so that's actually a reflection of the sunrise actually hitting those eastern slopes first and kind of increasing temperatures there a little bit faster than they would be if it was a westward facing slope. And also as you get towards the middle of the day, then the more steeply sloping sides, they kind of plateau and they start decreasing as you get towards the afternoon and into the evening hours. The other thing I want you to notice is that like the lower elevation stations have a much greater daily range than as you go up the mountain. And so as you get further and further, like the summit is basically the farthest from the surface, and the lower valley stations kind of see the most land. And so as you see more of the surface, that you get more radiation exchange. And so those temperature ranges actually get quite a bit higher than as you go up and up the mountain, you get much more like the free air temperatures range, which if you were actually at the summit elevation about maybe 10 miles to the east or the west, those temperatures are only varying roughly 1 degree Celsius per day versus on the summit, they're still varying about 2 to 3 to 4 degrees Celsius per day. Okay, next slide. Okay, so that was looking at a singular day. And then if you actually take those lapse rates and you look at them at a daily average over for different seasons, you can see that each of those, if you actually plot them on a plot like this, it's showing you how many days actually fit within that interval. So looking at the winter, so December, January, February, looking at, for example, the top left, that December, January, February period, you're looking at each one of those bars represents how many days actually were between those that lapse rate interval. And so you can see that during the winter time, you kind of get like a flattened distribution. So you have somewhat on the high side between between 5 and 7 degrees Celsius per kilometer. You got on the left side, but then you have to kind of have a long tail all the way to actually above 0. So like above 0, actually those will be your inversions. That's when your temperatures at lower elevations are even slightly lower than they would actually be on the top of the mountain. And so you can see that mostly it happens only during the winter months. And then you have on the right side, you have your transition seasons. You have the spring and the fall months. And so they kind of look a little, you got a little bit more humped distribution, a little bit more peaked, and they're kind of in between your winter and your summer averages. And your summer has got quite a strong peak, and you have a little bit less variation overall. So you can see that that is actually how it looks like by the seasons. And so like the fall and the spring are actually kind of a transition time between that winter and summer period. Next slide. Okay, and so if you're looking, so that was the seasonal averages, and you're looking at monthly averages. And so each of these rectangles here represent the different seasons. So the first one would be December, January, February. That's your winter season. The next one is your March, April, May. So it's your spring season. Then June, July, August is your summer season. And obviously September, October, November will be your fall season. And so you can kind of see that like between roughly May to roughly September, they have a pretty large range between your maximum temperatures and your minimum temperatures, or those lapse rates. And then the average temperature actually slowly slips down, whereas during the winter months, between like November to like February to March, those lapse rates, like those maximum, minimum, and average temperatures are much more tightly constrained. That the averages are actually pretty close, even though there's quite a bit of variation. And you can kind of think about this as more of like a frontal thing. So like as you're between like May and roughly October, that those the sun is very important during those times, and that like you're getting consistent swings between high and low temperatures based on the sun. Whereas between November and roughly March, the frontal system, so like warm fronts and cold fronts, are having much more effect, and they're actually affecting temperatures across the entire elevation distribution a little bit differently. Okay, and so like you can see that between those winter and summer points, you have like this kind of sharp transition. So like May versus April is quite a bit different, or also October versus November, you have a kind of a sharp transition on each side of those distributions. Next slide. Okay, and so just to further kind of, I guess, rehash this point a little bit. So these are actually 10-day running averages of lapse rates. And so you can see that during the red rectangle right here is like your summer mode. And then your blue rectangle on the right is actually your kind of your winter mode. So on your summer mode, you can have a very distinct separation between your maximum, minimum, and average lapse rates. And then during actually the blue rectangle, like kind of like winter mode, if you will, that those lapse rates are actually kind of all mixed and tangled. It's actually very hard to distinguish them actually on this kind of plot. Okay, next slide. And so looking a little bit more on the seasonal average lapse rates, and you also, this is just a bar plot of looking at kind of the same data, but just kind of looking at it a little bit more condensed form. And so I just wanted to look at you at the bar plot. So the purple bar here is the minimum temperature lapse rates. And you can see that those don't vary very much between winter, summer, and spring and fall. They're actually pretty consistent season by season, but you can see that the solar cycle, the maximum temperatures actually vary quite a bit between winter and summer. And so you can kind of see that the summer and the winter are kind of like the two endpoints, and then your spring and fall are a little bit more similar to, so like spring may be more similar to summer, and fall is actually more similar to winter. And it just seems to me, or seems to look at the data, that the mountain is actually looking a little bit more like a solar year, that it responds a little bit stronger to solar input. So spring being March, April, and May, you actually have a slightly stronger sun angle during those months than during the fall, which would be September, October, November. And also this matches kind of the modes seen, those 10-day rolling averages. Next slide. Going a little fast. And then finally, looking at the annual average lapse rates, you can always see that the maximum temperature lapse rates are quite a bit stronger than minimum temperature lapse rates. And you also can see that the very lowest elevations, looking all the way at like about 500 meters, that's your pink of notch elevation. And you can see that right there, that you can see a definite, at one square right there is probably due to frequent inversions during the wintertime. And then if you can see, look a little bit, like basically up to about a little over 1,000 meters, you kind of have a little bit of a skew to the right on between the average, the minimum, and the maximum. And that actually could be because that's about roughly the maximum inversion height, about the wildcat range. That's actually about roughly how high the wildcat range is. And that could actually be influencing the inversion height, because after it gets above, the inversion gets above that height, it actually could be spilling off to the east or southeast or northeast. And the inversion might actually not quite reach above that particular height. And there's also preliminary data that's suggesting that the lapse rates are actually quite stable over interannual timescales, so over that 7-year period, and that they're actually potentially greater when we actually have higher average temperatures versus If you have actually a little bit lower annual average temperature, they're actually a little bit less, so a little bit shallower over on the interannual timescale. Okay, next slide. Okay, in future directions. So if we have more data, we actually are looking into having stations going up the cog railway. So note the difference between the windward and leeward sides. It'd also be kind of cool to look at this in real time, looking at the formation of inversions, and also if that hypothetical wildcat range height is actually having an effect on those temperatures at those elevations. And you're also looking at the profile between, Jay actually would mention this a little bit in the introductory slides, that if you're looking at the profile, the temperature profile during precipitation events, it could be a better forecasting of where the freezing line might set up, and also real-time forecasting about where those ice layers might happen, also leading to better or worse avalanche forecasts along the mountain. And also to apply this data actually elsewhere to ecological research in plants and animals around the New England region. And that's all I have. So any questions?
Thanks, Karl. I really appreciate it. Thank you, Myah. Thank you, Jay. Thank you all for presenting your findings. I know we have some great questions that are already in the queue at the moment. And for those of you who are joining us through Zoom, would love for you to, again, to submit your questions, feel free to use the Q&A button that you'll find at the bottom of your toolbar. And feel free to submit any questions there, and we'll get to as many questions as we can. And we'll pass it around the room here a little bit, make sure that we have everyone's beautiful faces in there for some Q&A time. Well, without further ado, let's see, who do we go to? So Myah, if you don't mind me putting you on the spot a little bit, and anyone else who'd like to jump in for support. Kenneth asked the question, looking back at, just some of your work investigating precipitation on snow events, rain on snow events. So, I mean, what are some of the implications of your findings? Some of the motivations. How does this, some of this may connect from, say, like an impacts point of view from not only Mount Washington, but even beyond. Do you have any sense of that?
Yeah, so for rain on snow, definitely off the mountain, the increasing of rain on snow events anywhere where you can find a good enough snow depth can affect the ecosystem. So not only Mount Washington ecosystem could suffer from the decreasing of snow and just how things rapidly change in our environment. We could too look at other places where that have snow, where they're seeing that, okay, if there's not enough snow, how does that change the ecosystem for things? How does that change the neighboring people in the environment? And how overall will we kind of react? It's kind of the same kind of climate for warming temperatures and more precipitation. How does that affect the Earth as a whole? With people seeing with the monsoons happening in Asia as well, what is more rain overall on the planet? How does that affect us and all of that? So yeah, definitely with changing ecosystems and changing how humans interact as well with more rain, and the damages and severity of how this will kind of affect us as we see in the incoming years.
Thanks, Myah. Yeah, I know. I mean, even just from a regional perspective here, I mean, one of the threats of heavy rain on a lot of snow. I mean, there's a lot of liquid, or frozen liquid in this case, that's locked up in those snowpacks, and certainly, the river forecast centers and stuff like that around here in this region are looking out for flood threats and things beyond. And so.
In addition to recreational as well for our skiers who love to ski the higher summits as well. When's the best time for them to ski and when they can get kind of some good snow to even enjoy? I know that is one thing too that I've learned being up at Mount Washington. I'm not a skier myself, but I know that there is an importance for skiers for snow depth and to make sure that it's even safe for them to actually ski.
Yeah, for sure. And people that audience doesn't like seeing our time-lapse photos of snow disappear above tree line when Ryan Knapp or others might post multi-day meltouts in the middle of winter. So thanks, Myah. A question for you, Karl. It's a good science question here, one that researchers who look at big data sets have to think about a lot, and even Jay thinks about, and Keith and others in our mesonet when we look at data quality. Tim was curious, so why exclude outlier data from, say, the big temperature swing, the temperature ranges you had? Basically said like, hey, if it was above an all-time record high for the state of New Hampshire or vice versa for a minimum, why are you excluding that in this case when you're looking at this data set for your research?
So that's a very good question. For the most part, actually, when you're looking at temperatures that are that extreme, they're not just a little bit extreme. Like sometimes those temperature readings are like negative 800. And so those are probably not physical, that's below absolute zero. But the New Hampshire temperature extremes is kind of like a handy if it fits within that temperature range, usually it's an actual temperature, not a misreading of temperature sensor. Other researchers have used like those kind of temperature extremes to kind of standardize what data kind of gets included in that research and also what data gets excluded. And so those kind of temperature extremes would be a nice handy way of excluding bad data or outlier data. It's like, if it's likely that we actually did hit negative 55 or negative 60, and we probably would have brought that data to the Climate Extremes Committee and probably would have gotten that verified. And since we didn't, it's probably not true.
Certainly, things do happen to meteorological equipment, and there are many folks here at the observatory that can attest to things breaking in extreme conditions.
Yeah.
But let's see, another question. Let's see, I wanted to throw to Myah, if I can just find that question for you. Apologies. I mean, so I know Mike asked a question here for just general some of the increases you saw in like frequency counts and the seasonality of or excuse me, the climatology over time of precipitation on snow events. I mean, I know where your research is kind of ending up here. You don't have any necessarily, you're not putting lines of best fit or looking at trend lines yet, or that's not the stage that this project is at. But can you talk a little bit about, I mean, obviously, I think you were probably putting your, if you had to guess what that slope looked like sort of thing, but do you also have a sense of, next steps for, as you leave this project off to the next intern, where it kind of goes from there, and is, putting a line of best fit sort of thing in the cards here?
Yes, definitely best fit line, as you guys have mentioned before. In addition to determining what this precipitation type is, like I said, it really did kind of hinder us in trying to figure out if it was snow, rain, or sleet. But figuring out actually what is precipitating on this snow depth will make it easier for us to highlight rain on snow events. So this project can actually be, not precip on snow, but rain on snow. And we actually know, okay, because as well for rain on snow, what rain on snow overall is doing is causing to diminish that snow depth as it is kind of breaking down the snow particles and causing it to melt. And that's the decrease of everything. So trying to figure out if snow depth is decreasing is definitely our next moves, and seeing how rapid it is for the seasons, and also too how early it could be starting in the year, and or any other like kind of things that are standouts. And also, like I said, mentioned before, the other variables that kind of factor this into, Jay has worked with me and kind of coached me as well with talking about how the wind direction plays a really big factor on where this snow is landing. So that too is another variable that we actually need to open up and determine, okay, at what direction is this snow kind of flowing in, and what kind of changes do we see within those parameters as well?
Yeah, that's an interesting question around wind direction, and definitely a lot more data, that's for sure. But it'd be cool to map that out visually to see maybe some of those changes over time. Interesting, very cool. Thanks, Myah.
Mhm.
This is a great question here from Nina. Karl or Jay or whoever would like to jump in on this one. Yes, does the lapse rate impact meteorological predictions in the region? And if so, the values you captured are less than the world average. Do you think local meteorologists will start to use your data to help inform their predictions? Karl, what do you think? Jay, what do you think?
Karl, you can touch on it first.
Thanks, Jay. For the most part, I think I guess like TV meteorologists that would be looking at this kind of presentation would be looking at the base. So most people live down the valleys, and so it would be, I guess, of less use to them. It's looking more into the, once you get to like mountainous areas, you're looking at higher terrain. So I guess like maybe Jackson area, less people there, but they actually could be useful for looking at snow prediction perhaps up there. But the important thing, I guess, for the most part, I kind of glazed over this a little bit, but I was looking more at daily averages versus like seasonal to longer term averages, and didn't really delve into like how the fronts really influence temperature ranges, other than like, oh, the fronts kind of make it all kind of vary together, versus actually how that would be useful for like snow prediction, for example. And that would be kind of more of a, I guess, future direction for this kind of research, not something that I directly looked at. Jay, you want to chime in?
Yeah, so that was kind of the intent of the project, was to see if our near surface lapse rate is different from the atmospheric lapse rate, which we figured it was. A lot of places report that. But because of the modeling content and how that works, that they go with this atmospheric lapse rate. But interestingly enough, it would be really useful for ski resorts in snowmaking, right? Because
Yeah,
the air is really saturated and you have really high dew point. It's really hard for them to make snow. They usually just make ice. And they don't want to make ice because people don't like skiing on ice. But also part of that, it's part of like a bigger, grander scheme. So what you saw was the end of one synoptic project by Karl, after it's gone through a couple of interns, and then an observer has gotten to look at. And then the beginning of another synoptic project with Myah, where she started with some of the more basic variables, right? So we saw snow depth and precipitation counts, but it's interesting because if we see an apparent trend, right, there's no trend line, so that's what it appears to be at the moment, of this increased snow depth. Well, that would kind of infer that these precipitation events are more snow than they are rain, because we're having an increasing snow depth. So maybe we are not seeing increased in rain, but maybe we are and it's not affecting because we're seeing freezing rain events. Who knows? But it guides us into what we're looking for. But with Karl's project with the lapse rates, it was interesting for us to see the winter lapse rates in the moist adiabat line, because especially in the winter, you have those frontal systems where there's a lot of latent heat release, where you have water vapor that releases heat as it condenses into the atmosphere, which would bring those lapse rates down like that. And latent heat release is a massive component to the explosive development of our nor'easters in the winter. So there's far outreaching effects with the start of this. It helps a lot of climate change science with biology, looking at tree line studies, the AMC with our partners, and forecasting as well. So yeah, I think there's a lot of outreach to be had with this.
Excellent. Thanks, Jay. Thanks, Karl. I got one more question from the audience, and then I actually have one sort of surprise question for Karl and Myah. Sorry to give this to either of you. Well, the last question I want to ask each of you is just what surprised you the most? Well, what's something that surprised you about the research that you did, and even in Myah, in your case as well. I mean, the project was part of your internship, so I mean, feel free to elaborate. What surprised you about getting involved in this experience? But before we get to that question, one more for you, Karl. Kenneth asked an interesting question. Hey, for Karl, what's your prediction on how data from the Cog Railway side might differ from the autoroad side of the mountain? Because I think you kind of hinted at maybe some differences there, and yeah, curious for your take.
I think the most obvious difference would be, so on the eastward side, you're looking at the sun rising a little bit earlier, and so those temperatures are kind of skying up pretty quickly in the morning. And so I think on the westward side, you would kind of see a little bit like a lag, I guess, from east to west. But as far as like the overall trends, like the daily average lapse rate over the whole day, I would hope that actually they're pretty similar, because that means our data would be more applicable to areas in the White Mountains and also actually in the Hoosics and extending out into the broader New England region. And if they are different, that would be very interesting, but also maybe not so great, actually. But as far as things I would expect, I would definitely expect the temperatures to peak at different times. But for the most part, I would think the temperatures would actually be pretty similar over on daily time scale.
Interesting. Well, yeah, the answer is sometimes more complicated than you want it to be. Can't wish it away. Well, since I still have you talking, Karl, what surprised you? What was the surprise, I guess, that maybe stood out from looking?
I guess the biggest surprise I saw was when I did like the 10-day rolling averages, that like there was a definite, like, it almost seems like there was almost like a transition, like almost like a switch between like this winter and summer, like kind of variations in lapse rates. Like the summer being quite widespread between maximum and minimum temperatures, and during the winter, like kind of like almost the fronts kind of just sweep in, and suddenly temperatures vary very differently at all elevations at the same time, which is something I was not expecting when I started looking into this.
Yeah, you never know until you go digging. And thanks, Karl. And Myah, what about you? What was your surprise in all this?
So my surprise, we have two things, is definitely the snow depth. Before I came up to Mount Washington in May, I really wasn't too sure about how much snow we got at all. So definitely seeing the accumulation of like 30 inches and near 35 inches of snow depth was really like crazy to me. And to Alex's description of it always being a blizzard here, that enough and that alone was like, wow, I've never not really like been exposed to this information. So definitely seeing the amount of snow depth was surprising to me. And then in addition to the precipitation on snow accounts in class, as I've just graduated, as I mentioned before in May, we talked about the increase of precipitation and the increase of water vapor here on Earth as I took a climate class. Fall of last semester, but I've never seen it in practice. And that's what I love about this research, that it kind of brought the textbook to life. That's what I love to tell people, where I was able to see like, wow, okay, no, there's actually evidence of more precipitation on snow events here. So here is one small example where there is more rain that we're seeing, not rain necessarily, but there is more water vapor here on Earth that we've seen accumulating over the years to come. So those two things were very interesting to me as I get to apply my textbook, and then also just have a new experience and see more.
Well, Myah, thanks so much. I mean, we were lucky to have you this summer. Sorry we made you study snow in the summer. We'll have to have you back this winter. But seriously, thanks so much. We really appreciate everything you did for us this summer, and hopefully you took something away from it too. And best of luck down your path as well. And you'll have to come back this winter so you can see snow depth measurement in practice.
Yes, I look forward to it. And thank you as well.
Yeah, absolutely. Well, hey, thanks to all of you who have joined on to the program this evening. Thanks for joining Science in the Mountains. If you enjoyed tonight's free program, please feel free to support programs like these over at mountwashington.org. You'll see the donate button in the upper right-hand corner of the webpage there. If you have thoughts about future programs, thoughts about tonight's program, want to follow up as well with any questions we didn't get to tonight, there are a lot of great ones from all of you. Thanks for those. Please feel free to fill out the Google Form survey that'll follow this presentation here, and also in a follow-up thank you email. And then finally, don't forget, join us for our next Science in the Mountains program. It's on Tuesday, September 19th, also at 7 p.m. We're looking forward to hosting Dr. Jim Steenberg for the University of Utah, who will discuss the greatest snow on Earth with a closer look at what makes the Wasatch Range in Utah a world-class ski destination. So don't forget to register for that program. You can watch any previous programs you may have missed over at mountwashington.org/SITM, and we'll see you again soon. Have a great night, everyone. Thank you, Myah. Thank you, Karl. Thank you, Jay. Take care, guys.